Okay, I'm just going to start by opening up the drawing so that we're all on the same page here. Okay, so basically the last things that you guys have to calculate is this connection here, one of these connections, and one of these connections. So those are the last three connections you have to design, okay? And basically, the connection that you're gonna have here, of course, is gonna be the same connection on this side, the same connection on that side, and so on and so on. Okay, so in other words, whatever you have here, you're gonna repeat it all. Like in other words, this would be typical for all the connections on the long side. This connection here will be the same connection that you will do down here, the same connection you'll do down here, the same connection you do down here. And of course, this connection here will also be applicable to this side, to that side, because it all has the same value of CF. And of course, all these connections will also be repeated on the other side of the building. So you basically need to design only 3 connections, and those 3 connections will provide all the required connections around the outer perimeter of the building. Now, what I did is I went to ADA, and I'm going to give you, for this one here, okay, your VF value that you designed for is 363 kilonewtons. That's your VF value there. Here, your VF value for this one here, your VF value is equal to 40 kilonewtons. Okay. Now keep in mind that when you're checking the thickness of the column here, okay, when you're checking the thickness, here you're going to be attaching it to the flange. So here you check the thickness according to the flange of this column. And I don't remember what we have specified, but we sized this column. This beam was the same. No, this beam ended up being this beam that we have here is not this one. We have a W 410. When we designed this beam, this ended up being a W 410 by 39. That's the beam here. And when you're, because here what's going to happen is that the double diagonal connections are going to have to fit inside that column. And of course, since you have 40 on that side of the column, when you're checking the thickness of the web here for the column, you also have 40 there. So that's something you have to keep into consideration. And the same thing happens here. Here, the forces are very small. Here, the VF force for this connection here is 16 kilonewtons, very small, 16 kilonewtons. But again, the same thing applies here. You have 16 on this side and 16 on that side. And I believe that the column that we designed here, oh yeah, the beam is exactly the same beam that we had here, W200 by 19. So that's going to be the beam for that. That's the beam for that. So with that, you should have all the information to be able to design all 3 connections, because you have the size of the columns from our previous lectures or our previous labs. And now I gave you, and the only thing that you needed was a VF force. So now you've got all the VF forces that you need to design all 3 connections. I can't say more than that, unless you guys have questions.
Sir, I have a question.
Yeah, go ahead.
I can't seem to understand. I'm not sure if maybe explain, but like on this drawing in the corners, there's like a in parentheses, or there's like a minus 125, minus 250.
Okay. Like, first of all, I want to, like, the next thing I was going to talk to you about was the drawings themselves. Okay.
Okay.
So, but right now, I want to make sure you guys have all the information that you need to design those 3 connections. All I needed to provide you was the shear force you're designing for. I gave you that. So in other words, this is for the girder.
Yeah.
40 kilonewtons is for the long side, and 16 kilonewtons is for the short side. That's what you need to write down in your notes, so you have your VF value. Okay.
Wait, I don't get
That's
that.
okay. And then
16.
after that, as far as the beam goes, this is the beam that's here. That's the same beam that we have designed. And the only thing is that we don't have a 410 by 46. We have a 410 by 39. So that's the beam that you're going to be using to size your connection. So
Sir,
now, yes.
I don't get it. What do you mean 16 kilonewtons is on the short side?
In other words, right here, okay, right here, this beam is giving a shear force of 16 kilonewtons, and therefore your double angle connection here has to be designed for 16 kilonewtons.
But why is the other one on top 363? Is it not the same
Because that's
beam?
for Gerber. That's for this one here.
Yeah, but the one under is also a Gerber.
But I'm not pointing to this one. I'm pointing to here.
Ah, oh, okay, sorry. It's my fault.
No. It's Mason. I understand. Look, you understand? Like, okay, let me clear up the drawing because it's very messy. Okay, so just to start over. In other words, this is one connection here, Vincent. This has got the highest one. You understand?
Yeah.
Okay, and this is what we said, 363. I want to get this off ADA. Okay, this is 363. And I'm going to change color, so therefore you can, maybe that's what I'll do. Okay, so all of these are all the same. Okay, so now I'm going to change color. Fair enough?
Mm-hmm.
Then this one here, okay, this one here is the same as this one here, is the same as this one. No, sorry, there's no connection here. This one goes right over. Let me erase that. My mistake. Okay. So this one here is the same as that one there, is the same as that one there, the same as that one there, and that one there. Fair enough? And of course, all of these get repeated here, 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 and there. Good enough?
Sure.
And this one we said has a VF force of 16 kilonewtons. You can appreciate it's very small because this thing is only carrying just half of this little thing here. Then the third one was, let's make it in green, okay. And the third one was here, 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 you understand? And these ones here, right, we said that was on the wrong side of the beam. And we said this one was 40 kilonewtons, and that's what you designed that for. All I'm saying is that here where you have the two beams going back to back, when you're checking the thickness of the web member for the column to make sure it has the right material, remember that your VF force here is 80 kilonewtons. So you have 40 on this side and 40 on that side. So this thing has to resist both sides. That's all I'm saying. Okay? And the same thing applies to here. I'm sorry, like I should have made it in red for this. That's all I'm saying. And the other thing, guys, is that you weld to the column, right? You weld to the column and you bolt to the beam. So all the connections are going to be bolted to the beam. And the reason why you do that is, I'll show you. So let me talk about this column here, okay? I think we made these columns, if I'm not mistaken, they were I have to go back and look at I think these were W200s by 31s. I sent you the spreadsheet.
Yeah, that's what it was.
Okay? So if I'm looking at a cross section here, like this, okay, remember that you have a flange here and you have a flange there. Your two angles are going to be coming in here like this. Everybody follow what I'm doing? There's one on one side, and I should have made it symmetric, and one on the other side, right? Now, if I take 76s by 76 by whatever thickness I'm going to need according to my calculation, okay? 76 and 76, that already gives me 152. You follow? You're going to have to make sure that the space in here, okay, allows you to install these two angles. And if it doesn't install it, it's not a problem. Because what you're going to do then is that you have to go look at the geometry. And if you look at the column in plan view, I'm going to try to draw it up here. Okay, the column in plan view, you're going to have, for example, that little fillet there and that little fillet there. So you're going to have to take what they call the big K value, and that's what you're limited to. So if you're limited to that, you're going to take a 76, okay? You might decide to take something else. You might decide to take a smaller angle here so that it fits in here. Remember, what's important is that if once I'm welding, once I am welded, okay? Like this, okay, I'm gonna change the color so you can see the weld, okay?
Sir, sorry to interrupt, but what did you say was the W200 by 31?
What does it say?
What did you say that was a W200 by 31?
I sent you the spreadsheets for the exterior columns. Go look on
Yes, the
spreadsheet.
columns.
I know, but what are you talking about now? Like,
Like now what's happening is that in here, okay, if I'm gonna draw in here, I'm gonna draw, these are the angles, okay? This is the angle. In here I need to put an angle. You follow, the angles are gonna be supported by the web. So you gotta be careful to make sure that whatever you specify, this here fits within that space. So you choose your angles, choose them wisely. What I'm saying is that if you decide to use angle 76 by 76, let's say by 7.9, I don't know what you're gonna end up having, okay? This thickness, I don't care. What's important is to make sure that whatever you specify, it will actually fit here, so that when I put the, when I'm able to you know, to support these in here without it interfering with that little fillet. So you're gonna have to check that out. That's part of the design. Understand?
So this part is basically to find the angles, the angle connections between the columns and beams.
Well, I mean, you're gonna have to this first thing you do, just like with this morning, you're gonna be first worrying about what's gonna be the number of bolts I need to connect the beam, okay? The number of bolts. In other words, you get your VR, and then after that, you look at the size of angle, and then after that, you go to the other side, you determine the size of the weld, and then from there, you determine the thickness of the angle from the size of the weld, and then you take it from there. And then what I'm saying is that when you're choosing your angles, make sure you don't have a problem that it all fits inside your column. The same thing here. Here what's going to happen is that this is, for example, the flange of the column. Okay, this is the flange of the column. Now, if this flange happens to be 150 millimeters, I don't know what it is. I'd have to go look it up. I know what the size column is, so I have to look at the size of the width of this flange here. If I decide to use 76 by 76 steel angles, well, 76 is going to be out here and 76 is going to be out there. So how am I going to be able to weld here if I'm past the column? So that's something that you have to consider, that you're going to have to make sure that you can actually stay within on the width of this flange and be able to provide the welding so that your supporting angles can be welded to your column.
Okay.
That's all I'm saying. Like, so this is like, don't just like, if you just throw any angles in there, I can tell you right now, I know what it takes, but I want you guys to calculate this. You understand?
Sir,
Yes.
the VF you gave us from EDA, we don't divide it by 2, right?
No. This is the VF value. This is not the load on the beam. This is the actual VF value at that end of the beam. In other words, that's the highest VF value. In other words, I took this from quote unquote, you know, like for these beams here, I took this from load combination number 3, and this one I took it from the envelope. This is the highest one that the envelope gave me. Understand? 363 kilonewtons. So no, this is not like. And as a matter of fact, this case here, Gianfranco, let me just clear this drawing. Clear all the drawing. Here you have a cantilever, okay? So this is a completely different animal than what you have in the beam weld tables. You follow? So you wouldn't even be able to take the beam.
I wouldn't be able to use that table.
No, because here you don't have a simply supported beam. Here the beam is cantilever.
Okay.
You follow? Okay, so
Yeah.
you wouldn't be able to use that table. In this case here, you would have to determine what the biggest VF value is, or if you were actually designing these connections off of structural drawings for somebody else, you would have to ask the guy that actually designed the beam, said, hey, give me the VF value there. I don't need to calculate. Tell me what the VF is. So it's as if I'm asking you to design these connections for me, and I'm telling you, well, when I designed the beam, my VF value was 333 kilonewtons. Okay. Now, like a lot of structural steel drawings, when they have these, let's call it non-simply supported members that you can't get the load from the beam tables, the structural engineer will always give you the force near the column for what you have to design the connection for. And that's a good structural drawing. If he doesn't, he's going to get bothered because he's going to get called up by the guy that's designed the connection, and he's going to ask for the information.
Okay, makes sense.
So, like I said, guys, always think of your geometry and make sure that whatever you're doing, it conforms to your geometry. And now here you're looking at a very tight space in here. You're looking at a very narrow width in here, and therefore that's something you should keep in mind. And like I said this morning, guys, if you look at, we saw that when we're welding these two angles back to back, okay? When we're welding these two angles back to back, like this was one of them, here was the other, okay? Like this, okay? And then if you notice, like let me just change colors so we can, let me put some purple. If you notice that it was welded 2 times the thickness of the weld here, and then it was all the way welded down there, 2 times the thickness over here, and all the way down there, okay? So, and if you look at the VR value for this, okay, the VR value was the same whether this leg here was 76 or this leg here was 89. It made no difference for the resistance. Why? Because the resistance does not come from the width of the leg. The resistance comes from the length of the weld and the size of the weld. So I can take a 76, for example, and if all of a sudden, like for example, you might want to use like let's say, what's the other size down from 76? That's 2.5 inches. I'm trying to remember off the top of my head. 2.5, 2.4. Okay. You could use a 76 by 63 and make this like even smaller, because what's important is the weld that you provide, the length of the weld here, and it's not the size of the angle. And that's what I'm trying to make you understand. And if you can't find anything that fits, you can actually ask the guy to cut this to the size you want, and then he'll provide the weld. It's always going to give you the same resistance. So that's hello? Okay. So now, somebody asked me about the drawings, okay? Now, when you're doing a structural steel drawing, okay, the first thing you want to establish, okay, is this roof plan. Hello?
Huh? Huh?
Remelin, you're not muted.
Okay. Okay. Don't worry, I can mute people. Now, guys, okay, so here. See here, general notes, okay? Top of steel. Okay, this is one of the things you find. Some people put in the general notes, some people put here roof plan, and they put it underneath the roof plan. They can put top of steel. In other words, top of steel can be set at elevation 6,000. So what that means is that every surface that you're going to be placing on this drawing, okay, will be at elevation 6,000. So this way, when I come and put my roof deck on top, it's supported properly all the way across from one element to the other. Now, Joseph, you're the one that asked me what this is here. Who asked me about these little numbers here?
Yeah, that was me.
Okay, so basically, Joseph, look what happens, okay? This is my open web steel joist, okay? And I know that, I'm going to change color. And I know that my steel deck is supported on the open web steel joist. You see that, Joseph, so far? Right?
Yes.
Okay. Now, the open web steel joist here has a shoe. A shoe is where it's, okay, how it's supporting them. And this shoe here, depending on the size of the joist, can be either 100 to 125 millimeters deep. Okay, so if you want the steel deck here to be at elevation 6,000, Well, you better make sure that the supporting beam is 125 millimeters below your top of steel, so that when they come and rest this on the top of the beam, you'll end up getting your elevation 6,000. So this tells the manufacturer to how low or how high he has to place his members so he can achieve the top of steel that you want. Is that's not clear in your head, right?
No, it is clear.
Okay.
But if I'm not mistaken, I think at some places it said like 200. It wasn't always the constant.
Okay, but
No.
see,
It
here,
says
you notice
50.
here, Joseph, there's nothing, okay? You notice there's nothing here? Why? Because this beam is at 6,000. Therefore, when they're going to detail all that steel, they'll put all that steel at that top flange of that beam is going to be at 6,000. And then it's going to be at the same elevation now. Here, what happens is that in order to create these slopes, okay,
Right.
we need to drop the columns.
Yeah, I understand.
You understand? And therefore, this is to tell. So, what we did here is very simple. I got 1250 and 1250. Okay, so that's 25 meters. Okay, so 25 meters. The minimum slope that you should have in a roof is 2%. So 2% of 25 meters is 500 millimeters. So therefore, this column here, okay, will be dropped by 500 millimeters in order to create that 2% slope. So all of this is to tell the guy that make sure that this column, okay, by the time you detail this whole column and everything else, the top flange of my girder is going to be 500 millimeters lower than 6,000. So here, for example, is a high point. So therefore, this is all going to be at 6,000 here, and then you're going to start dropping to create your slopes. So now, if for whatever reason you want the member to be higher than your top of steel, of course, what you do is you just leave it as a positive value, and that means it's going to be above that elevation that you're building at. So negative means go below that much, below the level of my top of steel. Positive means go above it. So it all depends what you need to do.
Sir,
Yes.
why at the high point the exterior columns are still like all the exterior columns are at the same elevation? That's like flat all throughout.
Why? Because what you're doing is here. Let me just clear the drawing. Okay. What you're actually doing, is you're trying to create a basin. Okay.
Yeah.
You're trying to create a basin, and that means that. Okay, so for me to create a basin, that means that this is one side of the basin, fair enough. This is another side of the basin.
Ah,
This is
okay.
another side of the basin, and therefore the four sides of the basin are always at all the same elevation. You see?
But why are they still under the 6,000?
Where?
It says minus 125.
Which one?
Well,
The exterior
all
one.
exterior ones on the.
Oh yeah, that's because these ones, the beams are going to be put. I just finished explaining that because these ones here, the joists are going to be sitting on top of that,
Okay, that's why.
and that's going to make it 6,000.
Okay, makes sense.
You follow? So
Yeah.
here the joists are sitting on top of the beam, and the shoe is 125 millimeters high, and therefore this beam has to be placed at minus 125. So when they put the joist, the top of the joist is at 6,000.
I get it.
The smallest elevation, it says like at one point minus 300.
Yeah, but where's that? I don't know.
I don't know. Do you see
Go by
this?
this drawing. This drawing could be wrong, guys. I'm telling you what I expect you to do. I think most of it is right, but there could be something wrong with it. Don't take
Sir,
that. I didn't do
C2
this drawing.
C2
Look,
is
it was
300.
drawn by me. And when I checked it after the drawing was made. I didn't check it before.
Sir, C2 is 300.
Where's there?
C2.
300? No, I think
Yeah,
that's 500. That's not 300. That's a 5.
Oh.
I believe that's 500 and that's 250. Like I said, a 2% slope would give me minus, you have to drop 500 millimeters, and that's minus 500.
Even if it starts at minus 125, because that like from minus 125 to minus 500, that wouldn't be a 500
Yeah,
millimeter.
what you don't understand is that the top of steel here is at minus 500, right? And the top of steel here is at 0. Because the joists are sitting on top of the perimeter beam.
Okay.
You follow? So in other words, here, okay, here you want the column to drop by 500.
So it could have a slope.
Sorry?
So it could have a slope.
Exactly. So therefore, like when they're going to actually put this down and all that, the members are all going to follow and create the slope that you can drain your roof. And guys, the architects, you know, there is sloped formwork, sloped insulation that they can put on a roof to create certain slopes. You understand? But 90 to 95% of the time, the slopes are always created, especially in structural steel, even reinforced concrete drawings. The architect expects me to create the slopes for his drainage on my reinforced concrete drawings. Okay. So this is something that you guys should get into the habit of, you know, understanding. Well, 2% minimum, and therefore, and then you ask him, well, where are you going to be putting your roof drains? Okay, and then after that, you adjust your structure accordingly. Okay.
Sir?
Yes.
So at the bottom, it's going to be a steeper slope, I guess?
Well, it doesn't matter because you want to make sure the minimum slope is 2%. So, for example, in this direction, I get 2%, but in this direction, I'm going to end up getting 4%. Who cares?
Okay.
You follow?
Okay, so it doesn't matter that it's not the
As a
same.
matter of fact, I want to maintain a minimum of 2%.
Okay.
So here, if I get 4%, all that means that the water is going to run to the drain much faster than this one. It's going to run, you know, you've taken your, you know, Darcy's formula. You know,
What is that?
velocity of the water is dependent on the square of the slope, blah, blah, blah. So over 40 years, I haven't done that, but you understand?
Yeah.
So the stronger the slope, all I'm really doing is I'm increasing the velocity, and by increasing the velocity, I get more of a flow rate. Who cares? You understand?
Okay.
So for sure, like here, if I have, like for example, here I have 1250, here I have 25. I mean, 25 to 12,500 in this direction, 25. So therefore, in theory, this slope here is 4% in this direction. You understand?
So how do we know where to place that drain?
Where you have to create at least 2%.
Oh, okay. So it depends on the slope. Okay.
Exactly. In other words, you would work it out. Like, for example, the easiest way to create a slope is simply by lowering a column. And
No,
therefore,
but like horizontally on the girder, on that Gerber thing, like how do we know where to place it? Like we can just
you
place
always
it.
put it at the end. You always put it at the end of the cantilever.
Oh, okay.
That's the best place to put it because the cantilever can flex. You understand? Can deflect under the load, and therefore you want to make sure the drain is always. You understand?
Okay, makes sense.
Okay. So,
And
like,
sir?
I would never put it right here, right next to this very rigid point, because this thing will never deflect. So I'd always put it very close to the cantilever part of the Gerber. Understand? Like, ideally, if you look at this, you know that this deflects, you know that deflects. The ideal place to put it is right in where all the deflections occur. You follow? But it's very hard to go and create a slope right here because you have nothing to play with.
No, that makes sense.
You know, that would be the ideal location for a roof drain, you understand?
Yeah.
So, I mean, if you're doing a reinforced concrete, it doesn't. They can actually, you know, that really doesn't matter because you just tell them to slope the concrete there and you put it right there where you know this where the deflection is going to be the greatest. So reinforced concrete, I would put right in the middle of my panel and tell them to slope the concrete there. Okay?
Do you want us to show the calculations for the slope?
No,
Okay.
guys, come on. Don't tell me you can't take 25 meters and multiply it by 0.2 and tell me that's equal to 500.
It's just
Sorry, 25,000. Look, Mason, I'll tell you right now the calculation. 25,000 times 0.02 gives me 500. How's that?
Yeah, it was just you know, asking.
I want you to understand the drawing, understand, more than anything else. Okay, and I want you to understand that if ever you need to do this in real life, what you like, how you calculate. You guys, you've walked. How many city sidewalks have you guys walked on?
Too many.
Quite a few, right? You've all walked on city sidewalk?
Yeah.
No? You've never walked on the city sidewalk, Marco.
It wasn't me that said that.
Okay, I don't know. But somebody said, what do you think the slope is on the city sidewalk?
2%.
5%.
Oh, that's awkward.
See, it's minimum 2%, guys. The city sidewalk, they put 5% because they, sometimes the sidewalk settles. They want to make sure it's still, the water drains off the surface, blah, blah, blah. So if next time you guys are walking the city sidewalk, go to the edge and take a look, and you'll see there's about a good 5% slope in the sidewalk. Okay? Now, you shouldn't exceed 7% because on a city sidewalk, if you exceed 7% and it gets icy, then there's a danger of slipping. So there are minimum and maximums, okay, that you should keep in mind. And depending on the surfaces and where they are, I don't know which course they should teach about sloping, but I learned this, God knows where. But so I learned about my minimum 2%. I learned about my maximum. And there's also a maximum slope when it comes to drain pipes. I don't know if you guys know that. Understand? There's a minimum for drain pipes. There's a maximum for drain pipes because if the velocity is too high, all the shit paper stays behind. Only the liquid goes through. I don't know if they talked about that. So when it comes to sloping, guys, you understand? I mean, don't use 1%. I mean, 2%. As a matter of fact, in all interior parking structures, they always ask for a minimum 2% slope of the surfaces to the floor drains. Okay, so take the 2% for the rest of your life as being your minimum slope. And like I said, don't go over 5% if you're doing something like a walkway or that, because after that, on icy conditions, if you start getting to 7-9%, it becomes too slippery, very dangerous. So now, I think the drawing is pretty straightforward, okay? I think the only thing that, oh yeah, so guys, let me just, so these here, okay? These here, just so that we're on the same page here, let me just word my, okay. Now you notice that there's a tie joist there and a tie joist there, and that's to provide lateral stability for a column, and therefore at every column, okay. See, she put a plus sign, okay, and she said these are all tie joists, okay. Now remember that when we designed this Gerber system and we had tie joists, I mean we were laterally supporting the whatchamacallit, we were laterally supporting the girder because of the unbraced length. Well, this is wrong, okay. You only for the girder you only have to supply it on one side. So this is wrong. Okay. This is good for the column. This is good for the column, but this is wrong for. I'm sorry. One of these are wrong. So you don't have to for the girder. They don't have to be allowed to put on both sides, just one side. So I would take this one off, and I would take that one off. And this is good. This is good. This is good. This is good. This is wrong, and that's wrong. I'm just giving you, if you want me to tell you how I corrected this drawing, I'm going back now, okay? So that was the tie joist to support the girder. These are the tie joists to support the columns, okay? And if you don't do that, your column becomes very, very unstable. And believe it or not, I've been involved in quite a few collapses because people have not allowed to support the columns. And the rest, I think, is pretty straightforward on this drawing. Okay, don't forget your north arrow, okay? You should always have a north arrow on your drawing showing where and you should always orient your north of your drawing towards the upper side of your paper. That's good drawing practice.
Sir,
Yes.
do we have to put like the snow load and the dead load?
Well, I mean, you have to show your dead load and your snow load because you're not the one that's designing the decking. You're not the one that's designing the open web steel joist. So you have to give the manufacturer that information.
Oh, okay.
That's why you have to put on the drawing. Like you came up with a size so that when you'll probably come up with the same size, okay? And what's missing here, okay? What's missing here is, of course, she didn't put. I probably penalized her because she didn't put. Oh yeah, she did put it here. She shouldn't have specified the decking. She should just specify what is the depth of the decking and what are the depth of the joist. That should be specified here. In other words, decking depth 76 millimeters. That's what we decided. And we decided the open web steel joist depth was 900. And therefore, the manufacturer knows that he's going to take that as one of his constraints and apply these loads to design this open web steel joist. So she forgot to put that information down. Yeah. Anyways, I'm trying to, as I'm going over this drawing, I'm trying to remember what else. might be right around the drawing. But overall, I mean, the drawing's pretty good. Nothing wrong with it. Now, guys, you don't have to do this. You can put open web steel joists here like this, and then take an arrow and go all the way down here and point here like this. And that means that all of these are open web steel joists. Well, once you put open web steel joists here, you can, in lowercase letters, you can write the word do, okay? And do all the way across. That means repeat what you see here all the way down here. There's 3 ways of doing this, okay? So in other words, one is simply putting open web steel joist right across the page, putting it once, and then taking an arrow showing that this is all the way down. Or you specify once instead of writing. Now, the reason why they used to have do before is because it's much faster essentially to write a 2-letter word. And for example, if you had here a W 350 by 530 by 82 and repeat it, so that's why they came up with the shortcut of do in the old ways. But today with AutoCAD, well, that's no longer a concern when it comes to graphics. And I guess that's it. So now, do you have any questions that you want me to answer?
Yeah, I have a question about what we have to submit to you.
I have it all on the outline.
Right. So regarding like the spreadsheets that you've supplied us with for the Gerber system, etc.
For the Gerber system, I don't expect you, because you're not at school, right? I don't expect you to submit anything because you don't have access to your file anymore. You follow me?
So we specify what the beams are that we're using in the Gerber system on the drawing, and that's good, or?
Well, I mean, like, yeah, for the Gerber system, for the Gerber system, you can give me a copy of the spreadsheet, how we designed the Gerber system, yes. That I gave you, understand? But I don't expect you to give me the ADA analysis of the Gerber system.
Okay, so those spreadsheets that you provided us, we have to include that in our calculation package.
Yes, of course, yeah.
Okay, and like for the base plates for the exterior columns, those spreadsheets in our calculation
package. Yeah, I'm going to go over that right now. I've got that now, and I'm going to be sending that to you guys because I'm going to show you what I did and so you guys can follow what I'm doing. Understand?
Okay.
So, like, that was the last spreadsheet I needed to correct. Somebody asked me for the size of the base plate. And I think it was last week, I went over it and I corrected the spreadsheet, and I'm going to open that up next. But I just want to make sure we're all on the same page here when it comes to, as far as the last few connections you need to do. You've got all the information now. So there's no need, like I want to make sure you had all that in hand. And at the same time, I want to go over this drawing so that you guys have pretty much know what you're doing. And then next week, what we can do is that maybe you can already have enough on your plate. So just worry about designing the connections this week. Get that over and done with. Understand? And then the next lab, I'm basically just going to go over the last 3 drawings to make sure we're all on the same page.
Sure.
Okay. Yes.
So like the Excel sheet, the Excel file, there's 3 sheets on the file. You only want us to give you the last 2, or?
The one that you're choosing as your design.
All right.
I don't want to see all the trials. I just want to see the one that works. Understand? Like, for example, I think for the column, we tried like 5 trials, and we finally came up with one that worked. So I want you to give me a copy of the one that worked. I just want, like, exactly, just a copy of the sheet that works.
All right, so like the middle sheet or the 3rd sheet.
I don't know what sheet it is.
I'm talking about the sheet with all the explanations. You don't want that.
Oh, no. That's for you, so you guys can relate to those equations and how we developed the spreadsheet. No, I don't exactly. You're talking about the general information sheet? No.
Yes.
That's for you, okay? So that you can relate a little bit more to what the spreadsheet is doing for you, or like how elaborate those calculations could be. You can only do it on the spreadsheet.
Sir?
Yes.
I have a question about what we did last week.
What did we do last week? Yeah,
with the vertical brace connection.
Yeah, okay.
Okay, so we didn't do anything about the gusset plate. Like, do we have to do the welding of the gusset plate and the size of the gusset plate?
Everything, yeah. You've got all that information now. You should be able to size the size of the gusset plate, how much welding is required, and then also how much welding is going to be, and then you have to connect your gusset plate to your structure.
Okay, so we just do it the same way like we did the plate?
Yeah,
the plate
exactly.
that's connected.
Yeah, the gusset, like in other words, whatever size plate you determine for like for example, I don't know what you got as a plate for your HSS connection. It's the same thing as the plate you're going to be using as your gusset plate. Yes.
Okay, so if I used 6 millimeters for the other plate, I could use 6 for the.
Yeah, because if 6 was good for the gusset plate, for the plate for your HSS, that means all the bearing and everything else is good. Then it's going to be good for your gusset plate. And all you have to check, the only thing you have to check for the gusset plate is make sure that the thing doesn't shear out. Understand?
Oh, with that long equation.
Oh no, I mean the long equation. Here you have AGV, right? Yeah, right. So
Yeah.
you're gonna have 2 holes in your in your gusset plate. I don't know if you have your holes this way.
Okay, so we're checking the bearing.
No, yeah, you have to check the bearing in the gusset plate, but you shouldn't have to worry about the bearing in the gusset plate because you've already checked it here on the HSS. You had to check the bearing on the HSS, so the bearing would be the same if you're using the same thickness. The only question is that, like, let me just clear this so that we're on the same page. So, for example, if you're going to have some kind of a gusset plate here, like this, right? Now, how are your holes? Are they like this in your gusset plate, or are they like this?
Yeah, they're like that.
Okay, so if that's it, then you're going to have to check the tear out here instead of the block shear.
Okay.
That's all you have to check. So in other words, make sure you have an edge distance here. Put at least 35 millimeters, whatever you need, right? And then this spacing here. So this is in tension. This here is in shear. And therefore, you can calculate the long equation exactly.
And the weld size, we can use the same weld size as the plate.
Well, no, there's no weld size here. You're bolting. You're bolting your brace to your gusset plate.
Okay, so we don't have to check for the welding on the.
There's no weld because you're welding here like this. Here, let me just change color.
No, I'm saying the welding of the gusset plate onto the column like that.
Oh yeah, here you use the same size that you use. It's going to be over designed, but you don't care. Use whatever.
Okay.
Like in other words, whatever you shows there, do the same thing here. Just exactly. Okay, you're talking about where you're welding the plate. Yeah. Use the same size weld.
Okay, perfect.
Okay, but you understand here what you're doing right here?
Yeah.
Okay.
Yeah, that okay.
I'm sorry. When the gusset plate, I thought you were talking about welding the gusset plate to your brace. You're talking about welding the gusset plate to the structure.
No, it makes sense what you're saying. Yeah.
Okay, no, that makes a lot of sense.
Okay, thank you.
Okay, guys, I'm starting to see the end of the light of the tunnel. I don't know about you guys, but I'm gonna have a lot of stuff to correct. So who cares?
Sir,
Yes, Emily.
I had a question on the second drawing.
The second drawing. Yeah, but we're gonna go over the drawings next week, okay? Because I think you have enough on your plate right now that if I even go over it, like I think you have enough on your plate that you can worry about doing your connections and whatever else, and then whatever you're not sure about the second drawing, I'd like you to save it next week because I think people are just gonna forget it between now and next week. If you don't mind, understand?
And if we want, because you mentioned a couple weeks ago that we could like send you our drawings before we submit it.
Yeah, but they got to be like this complete. You understand? That's what I mean by sending them to me. You understand? When you think that I received drawings and they were way too preliminary for me to comment. Understand? So if you're going to send me, for example, I put my joists in and I put my beams in and this and that, they better be 95 to 98% complete, and then I'll comment. But I will not comment on stuff that you're developing. I expect you to develop it. You follow?
Yeah.
So, you understand? Like I don't mind reviewing stuff, but I will not, for example, if you haven't indicated where your details are, like if your drawings are not if you're like, you can send them to me, and if I think that they're still very preliminary, I'll just send them back so they're too preliminary for me to comment. You see? But what I mean is that they should be as complete as possible. And then I'll be more than happy to go over them so this way you can tweak whatever you need to tweak so you can, fair enough?
Yeah. And also, other than what you mentioned about the depth of the joist and the open web steel joist,
Yeah, those are the notes that you have to put on the drawings. They're missing here. We did that at the very beginning of the semester. We decided what was going to be the depth of our steel deck, and I think we decided that it would be a 76 as opposed to a 38 millimeter depth. And we decided that the joists were going to be 900 millimeters in depth. Okay.
I was wondering, is there anything else that you can see that's missing?
Right now, not off the top of my head. Sorry, Emily.
Because I'm not too sure, like, about all the notes that we have to put for steel and for wood.
Well, let's worry about steel for now, and then next week when we go over the wood, we'll worry about the wood drawing. You understand? The wood, like I said, the wood has probably a few less notes than the steel. I think I already talked about the wood notes a bit in the past somewhere, but so like I said, don't worry if you're missing a note. That's not going to hurt you. Understand? Like, you know, if you get the drawings to this percentage complete and you end up forgetting about one or two items, trust me, you'll get near perfect for the drawing. Follow?
Yeah.
So I know like you guys are, I'm really proud of the fact that you guys are striving for perfection, which is what I want you guys to try to do. Understand? So I'm proud of that. So, and I will help you to achieve that perfection to the best that I can. Right? I just noticed that your circle here was a little bit off. Okay. Now, guys, this is like these graphics here. Okay, this is, you know, it's up to you. If you like doing them this way, if you have a better way to do them, okay. You know, I have, you know, this is just a nice way of circling the detail. Like again, this is the detail number. This is the sheet that it's on. Yeah, that's right. And yeah. So okay, so if there's nothing else on this drawing, I like to go onto that spreadsheet, and I'm gonna forward it to everybody regarding the exterior base plate. Okay, I'm just gonna go over it so that you guys have an understanding of what you're looking at, and I'm gonna stop sharing this unless somebody else wants to jump in last minute and ask me something in particular regarding the connections or this drawing here. Everything's good so far? Okay. Now, where is, okay, here we go. Okay, now, if you remember, I had shown you the spreadsheet in the class, right? And so this was just to give you an idea of what happens when you have a bending moment, okay, as well as an axial force. So it's very simple, okay? It's like, I want you guys to have an understanding of what's happening. So basically, when you have a bending moment here, okay, so one side is in compression and the other side is in tension. So therefore, it can happen that this bending moment is so high that this thing doesn't even want to touch the concrete anymore. It actually wants to lift off the concrete. And therefore, anything that you use here to calculate the bearing resistance of concrete doesn't provide any bearing resistance, and therefore what's really happening is only part of the concrete is offering some bearing resistance, and that's what these formulas do. Now, when you look at this type of situation, there are two situations. One where if you have the eccentricity, okay, fall within what they call d/6. Now, d is the size of your base plate, okay, and divided by 6. In other words, if your eccentricity falls within this distance here, d/6, then you have one situation, okay? I don't know if you learned this in soil, but this is called fall within the middle third of your base plate. That's another way of saying it. And, okay, now here, what I did is that I took the size of the column that we determined on the outside. I took the CF value that we had for the column. This is for the long side, okay? And I took the MF value that we had for the MF value and all that. This was the strength of our steel, and this was the strength of the concrete you guys decided to do your foundations out of. I start plugging this all in, and then all of a sudden I come down, and guess what? Okay, I'm sorry, I shouldn't do this one. I should start with this one. So I started with this one, okay? So what happens here, when it happens to fall within the middle third, you end up getting a little bit more bearing here. So I put in all the values, and without even worrying about it, I go down here, and guess what? It's no good. In other words, this is the maximum eccentricity you should have for d over 6, and this is the eccentricity that this situation gives me, okay? That means I wouldn't even be able to use this method of calculating my base plate because my eccentricity falls outside the middle third. In other words, okay, so that means that the eccentricity falls outside that middle third here. So therefore, it's out here somewhere. So this is the eccentricity, and it falls somewhere out here, okay? So that's no good. So therefore, I don't have a situation. So there I have to go to what they call a case number 3 situation. And of course, a case number 3 situation is this one here. And here, this becomes a little bit more difficult because everything is by trial and error. You start with a certain number of bolts, a certain number, because there's 5 variables. There's no one equation, one unknown. This is 5 variables, so you start fixing a couple of variables and see how the other ones pan out. And that's why this is like a game of going through a number of iterations until you converge onto a solution. And that's why it's kind of hard for me. So here what I did is I started with the same values I had for case number 2, the CF value, the MF value, and all that. And I start. Now here I put an A2 or A1 ratio of 1 because you're sitting on the wall, okay? And basically, so these are the values I'm designing for. Here's my eccentricity. And these are the equations. I'm sorry, I'm going back to case number 3. Sorry. So these are the equations. So all of a sudden here, my eccentricity exceeds d over 6. So I'm using this, okay. So here what happens is I have to guess how many bolts I want to use. I have to, not guess, but select as a trial section, how many bolts I want to use. What's the diameter of bolts? And of course, this is just the area of the bolts times 2, okay. And then I have to choose what width of plate I want to use. I have to narrow that down. This is no longer, this becomes the strength of the steel and so on. And then all of a sudden, I use this equation to calculate my D, okay? And I see that the D is okay. And after that, once it finalizes my D, it goes down, it calculates the that overhang there, which we call M and N. Well, here they call it L, okay? And it just checks to make sure I'm within the whatever I assumed up here. This is pretty close, so as far as I'm concerned, this is okay. And this is the equation that we use to calculate the thickness. And after I've gone through a few iterations in here last week, I end up getting a plate thickness that needs to be 16 millimeters. So therefore, we can say all the exterior base plates can be 310 by 150 by 16 millimeters thick. And and what I want to see in your calculations is just a copy of this spreadsheet. That's it. Fair enough. And I'm going to be sending this to you guys either today or no later than tomorrow.
Perfect.
Okay. So, I mean, the first time I did it, we weren't even sure about the size of our columns. We weren't sure about these loads here. And then as we started to fine tune the exterior columns, and as we started to get more and more the values on the exterior column, I was able to come in here and, fine tune the requirements for the exterior base plates. Like I said, guys, it's, I mean, I don't know if you can see it in here, but where is it in here? Like, where is it? So here you have 1, 2, transit the 5 variables I was talking about. Oh yeah, here. Yeah, that's a good one. 1, 2. Okay, that becomes a variable. So you can appreciate to calculate your D. It's like there's 5 variables in here, and once you start fixing a few of them by iteration, you can start solving this equation. And that's you know, and that's all I wanted to show you, that as far as the base plate goes, not for the exterior columns. And use the same ones for the short side as it for the long side. And, I don't think I did it for the short side, but I'm pretty sure that we'll probably get something very similar. Okay, so I will be sending you this, not a problem. Okay, and that's where you get your values here for the size of your base plate. Hopefully. Now, is there anything you guys want me to go over? Or do you guys want to run off and do the calculations for your double angle connections? Because that's not something I can do. Okay, so if we were in the lab right now, I just let you guys work on your double angle connections, and get any questions, I'd be here to answer them. So, is there anything else you want me to talk about?
Sir, can you talk about the vertical brace on the gusset plate? I don't understand it.
The vertical plate on the gusset plate. Oh, the vertical brace. Okay. Well, okay, let me just. Okay, so we done. I'll do a stick drawing here. Okay, so here I have a column. I'm doing only. I should. Yeah, I should do this. I have a column here. I have a column here, and I have a column there. I'm doing okay, and here are my vertical braces. So far, so good?
Yeah.
Okay. So last week, what we talked about is we need to be able to, for example, we decided that these vertical braces were going to be HSSs, right?
Yeah.
This. And we were going to slot a plate in here like this, remember? And we're going to have a couple of holes in here. Remember that?
Yeah.
And whatever you do here gets repeated here. So in other words, that detail will be, so in other words, this one here would be here, 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 and here. Agreed?
Yep.
So far, so good?
Yep.
Now, when you're, excuse me, you're going to need to connect your brace to your structure. You agree?
Right.
Okay. So if I look at my structure, now let me change color so that we can, what color did I make? Okay. Here is my wing column. I'm sorry, not my wing column. My wing column here, but here's my column. Let's look at this column here, right? Fair enough. This column is going to be anchored into my foundation. Do you follow?
Yeah.
Okay. Now, if I make a cross section looking down here like this, okay, this is what I see. I see the flange, I see the web, and I see the flange, and then of course I see my base plate. Do you agree?
Yeah.
Okay. Now, I'm going to change color, okay. I can put a gusset plate in here. That I can weld to my column and weld to my base plate. Now, I'm going to do another cross section so you can see what we're talking about. Let me make another cross section. So, I mean, this is, okay. I'm going to make a cross section across here now, okay? You follow what I'm doing?
Yes, sir.
Okay, so basically, if I do a cross section across here, is I have the back flange here like this, right? I have my base plate like this, and I have my web in here. So that's looking right across. You follow? Now, if I go back to my purple, so you can see the base plate. So the base plate is going to be, you'll be able to put a base plate in here like this, and then at an angle here and like this. You follow? And then you'll be able to attach your base plate. You can be able to weld it here and weld it here. And then you're gonna have your 2 holes in here, whereby you'll be able to take, for example, I should have drawn this. See, like down here. Okay, your 2 holes in here, so that you can take your 2 holes in here and attach your bolts and attach it to your gusset plate. What I should be erasing here is that you don't see this anymore here. Do you follow what I'm doing, Sylvita?
Yes, sir.
Okay, so that's where, so you have to look at, so here, on this side here, okay, what's happening is that, like up here, okay, up here, if I'm gonna, so I can erase this, Sylvita, everything's good? So do you follow what we're saying, like the gusset plate here? So this gusset plate here will be the same gusset plate here. Fair enough? Now at the top, you have another situation, okay? At the top, it's very similar to the bottom, that instead of having a base plate, you have a cap plate. Because at the top, this, I'll show you that. Let me erase. Okay, so let me erase this. Okay. At the top, I'm gonna do it. What color is this first? I like to make it blue because I make all my structure. Make it blue. So at the top, so this line represents the beam. And this line, in other words, this is the beam that's sitting on top of my wind column. So far, so good? And, okay, so here, to connect, to support my beam, remember I told you that whatever base plate you put at the bottom, you should put it on top. So in other words, I'm gonna have a cap plate here of 16 millimeters, okay? Like this. And then I'm going to have my column that's sitting here, like this, okay? So in here, I'm going to be able to do exactly the same thing. I'm going to be able to take my gusset plate and weld it to my cap plate and weld it to the flange of my column, and then that's going to be my gusset plate in there. So this gusset plate is the same as that gusset plate, the same as that gusset plate, same as that gusset plate. So you're just looking for areas where you're just looking how you're going to be able to transfer the force from your structure into your brace down to your foundation. So in other words, what you're looking at doing is you're looking at, okay, so you want to make sure that, for example, when the wind, whatever, the lateral force is coming here, okay, it goes through your roof diaphragm and then it hits here. It's going to go through the connection here and then go through this connection here. Yes? And then all the way down here through this connection here and eventually get transmitted to your foundations.
Okay. All right. Yeah, that makes more sense. So basically, if you design for one gusset plate, it should be adequate for
everything around. Yeah.
Perfect. Thank you, sir.
Because like basically, well, here if you want, you can make this cap plate the same thickness, but the geometry can be slightly different. Like you don't have to make it, but as far as your cap plate goes, because what you're going to do is you're going to be bolting it there and bolting it there. See? So this is going to be bolted together, and therefore that's how the force gets transferred across these bolts, into these welds, into the brace, you understand? And that's how the whole load path gets transferred all the way down to your foundation. Now, I'm not going to let you, like, in theory, this anchor bolting here, if you were designing this anchor bolting here, you would have to calculate the tensile force that is going up your frame and make sure that the bolts here can actually resist and create a downward reaction. But that's another story. Okay? But we're not going to go there. So, is that a little clearer, Suvitan?
Yeah, much clearer. Thank you.
Okay. So that should clear up the. I'm not sure what they did on the drawing, but we'll talk about the drawing next week, and we'll look at it, see if it's done right. If it's not, I'll correct it. So at least you guys will have the right information. So Anything else you want me to talk about at this point? You guys feel comfortable that you're able to handle it all? No, not a problem? Okay. Well, in that case, I've got nothing else to say, guys. The rest is, the rest is up to you to do the work and to do their drawings and so on and so on. So,
Sir, can we go over, can you let me know when we can talk about the wood project?
well, if nobody else has any steel questions, I was going to suggest, right, Emily, that we talk about that right now.
Sir,
Yes.
I just wanted to know which assignment is going to be on the field.
Which assignment is what?
On the field test.
I don't know. Everything that we covered after the last test. How's that? Guys, I don't memorize assignments, you understand? Like, you got to remember, I've got 3 courses in my head, you understand? Like, the wood assignment numbers don't correspond to the steel assignment numbers. They don't correspond to my structural analysis. So don't ask me assignments. Ask me, like if you ask me what we need to design, you're going to have to design, for sure you have to design a bolted connection. For sure you have to design a welded connection. And for sure you're going to have to design a double angle connection. How's that? Is that easy? It's easier for me to tell you you're going to have a bolted connection, a welded connection, and a double angle connection. And I'm pretty sure the assignments, so in other words, what was the last assignment number that we gave today? Number 7? Is that what it was today? I'm trying to remember.
Corrected 6, and assignment 7 is due next week.
Okay, so in other words, if I go by that, then most likely you should review assignment 5, 6, and 7 for the exam.
If I'm not mistaken.
Pardon? Oh, no, I'm just, like, if you're mistaken, then you're leaving me the mistake. But I'm just saying, if the last assignment was number 7, then it would be 5, 6, and 7 for the steel. Okay, in other words, just remember, a bolted connection, so I think that was assignment number 5. A welded connection, that was assignment number 6. As a matter of fact, the bolted connection and the welded connection are going to be one continuing to the other. In other words, I'm going to ask you first to design it as a bolted connection, then redesign it as a welded connection. And then the last one's going to be a double angle connection. I'm not sure which one I'm going to ask you. I'm going to ask you bolted to the beam, welded to the column, welded to the column, bolted. I don't know. That I'll decide soon, right after. Like, matter of fact, I was trying to prepare the wood test this morning, and then I stopped doing it. So, because I think the wood test is before the steel test. So I was working on the wood test to see what I had to prepare in terms of handouts and all that. Okay. So, but I think we decided hold on, I have made myself a note here that the steel test on the 14th and the wood test on the 11th. Yeah. So I guess you're all ready for the wood if you're only concerned about the steel, right? Is that it? Okay. So, like next week's class in steel, I'm just going to be correcting the last assignment, and I'm going to just leave it open to you guys if you have any questions. Otherwise, I don't know what else I need to be able to talk about. The lectures are over. Okay. Okay, so if there's no more steel questions, Emily had a wood question. For those of you that are interested, you might have the same problem, so you might as well listen in, and I'm going to talk to Emily about it. Okay. So.
Sorry, sir.
Yes.
I have a quick question about steel.
Okay, go ahead. This is a steel lab, so steel takes priority over wood. So, go ahead.
It was just about when we're verifying web crippling.
Oh yeah, okay.
And I just wanted to understand what the value of n was in one of the formulas.
N is the length of bearing. Okay. So, for example, this is my beam here. Okay. This is my beam in elevation. Matthew, you see what I'm drawing? Okay.
Mm-hmm.
Now, so I'm going to change colors so two different. Okay. So, for example, if I happen to have a cap plate here underneath my beam, which should be the same size as your base plate, and my column is sitting here like this, fair enough.
Mm-hmm.
The length of this bearing length here, it's really the bearing length. This here this length here, I don't know what you have, but let's say if your column is 176, this should be in the order of about 240. Is that what it is? I don't know. But you understand this length here, L here?
Mhm.
Well, that's your
Mhm.
N value.
Okay.
Okay, so in other words, whatever you design your base plate for, right? Use the same dimension for your cap plate and take that, because it's going to be a square one, and therefore this is your N value in the web clipping, the length of bearing.
Okay.
Okay?
Yeah.
Okay. So that's
that makes things a lot clearer. Okay. Thank you,
like, for
sir.
example, if you like, I'm pretty sure that if you didn't have a cap plate and you just took the size of your column, most likely it would work. But the real is the length of this bearing. In other words, see, if from here to here is where the web would start crippling. You follow?
Mm-hmm.
So that's why you take this as the value. So therefore, it allows for more area to be distributed, more of that force to be distributed over a bigger area, less of a chance for it to cripple.
Okay. Makes sense.
Okay? And that's what the N value is, the length of bearing. I know it's weird.
Thank you, sir.
It's weird.
I know, but it makes sense after explaining it.
Exactly.
I understand.
Now that you see it and you try to solve it, it clicks right away, right? So, okay, and the nice thing about it is that I think they want you to take what, just the N value, right? And that equation is just for interior columns. When you have exterior columns, it's another equation because you don't have the same situation here. So that equation, web crippling, Matthew, only use it for interior columns. Like in other words, where the member goes right across, okay? Not for exterior columns.
Of course.
There's another way of calculating for exterior columns.
Okay.
Okay.
Sounds good, sir.
Okay. Yes. Sounds good. So guys, this is what I mean. Like, if you have any little glitches that you are coming across as you're doing your stuff, you know, I'm going to try to clarify it as we go along. Now, if there's no other questions, Emily is having a problem with one of her gusset plates, okay? And so that let me just see if I'll draw this like this. So Emily, the question you asked me was this, okay? This is my bottom chord here. And this is my top chord here. Agreed? And you're asking how to size the gusset plate so I can join the bottom chord to the top chord.
Exactly.
Okay. So first thing we start off with is number of nails required in your joint. What did you determine that to be?
I think it was 30.
That little? Are you sure? Well, first of all, what was the T? Well, yeah, probably. What was the TF force in this member right here? Do you remember?
Hold on.
If you give me the TF force, I'll tell you the number of nails.
Yeah, no, I took the wrong TF force because basically the number of nails at E, I took it. I put that. You can add that.
Just give me the TF force in the member.
I don't have it.
Okay, I don't have it either. Okay, but anyways, look, you need to know the number of nails, otherwise I could just start you off and then you end it off.
Well, can we say let's say 54?
54 nails?
Sure.
Okay, let's say that we need 54 nails, which is very reasonable. Okay. Now I noticed that in the what you sent me, okay, I think you're assuming that this is a 2x6, and is this supposed to be a 2x4?
In my calculations, I have 2x6 because for me it didn't work the 2x4 because it was like a little bit over. So you said that we could either choose to use a 2x4 or 2x6, and I chose a 2x6.
Okay, well I'm going to do it for a 2x4 because everybody else is doing it, and it won't change much. Okay. I'm going to do it for a 2x4, because most people are using a 2x4. Is that okay with you, Emily?
No,
Okay.
no problem.
Okay, so I'm going to use a 2x4, and okay. Now, so you need to put 54 nails, right? Now, we've talked about this over and over again. We know that in a 2x4, we have ample room to put 3 nails in a row. We all agree, right? And Emily, for a 2x6, I'm not sure, but you were able to put 4 nails in a row. Is that it? Pardon?
I was, yes.
Okay, so if you're putting 4 nails in a row, it doesn't change much. In other words, you're just gonna have more nails per row, right?
Mm-hmm.
Okay, so in other words, you're gonna have, if you're gonna have 4 nails per row, in other words, you're gonna have 1, 2, 3, 4, right? And then you're gonna have 1, 2, 3, 4, right? So here you're gonna be able to put an extra one in between. You'll be able to put an next one in between, and you'll be able to put a next one in between. So that's what you end up getting. You follow?
Mm-hmm.
The distance between here and here, this is 60. And the distance, and then of course, like these, you're keeping your edge distance, and you figured out that you can put 4. Okay, so in your case, you're able to put, like we're able to put 1, 2, 3, 4, 5, 6, 7, 8. You're able to put 11 nails, whereas we're only able to put like 5 more nails because you're using 2x6. So Emily, you know that you're working always parallel to the grain. So you know that from here to here, you have to maintain at least 40, right? And then here you have an edge distance of at least 13. Okay? Now, of course, if you work out your geometry, that means here you have another 40. So these nails are going to be slightly angled with the angle, that this mitered angle that you have here between your bottom chord and your top chord. Do you agree? But that doesn't change anything, because, so in other words, here you have 1. I'm going to change color so that we can see it a little bit clearer. Okay, so in your case, you're going to have 1 nail. I'm going to do it for your case. 2 nails, 3 nails, 4 nails, okay? 1 nail, 2 nails, 3 nails, 4 nails. Then all you're going to be doing is that moving over by another 60 millimeters, you're simply going to add another row, right?
Mm-hmm.
And then you're going to move over by another 60 millimeters, and you're going to add another row. And then in between, you're going to put your 3 additional nails. So far, so good?
Mm-hmm.
So therefore, that means that up to here, every time, okay, so where did I put my 60? Here's my 60, right? So here, so every time I add a row, in your case, you end up getting 1, 2, 3, 4, 5, 6, 7, 8 nails, right?
Mm-hmm.
So what's 54 divided by 8? You need 7 rows approximately. You follow what I'm doing?
Yes, I do.
Okay, so that means that if I take 60 times 7, I end up that I'm going to get all the way out here to approximately, from here to here, I'm going to have approximately 420 millimeters. And then I'm going to keep an edge distance here of 40, and then distance to my gusset plate. You follow? And then, so now I would take the furthest distance here at 40 here, and then I would simply go straight up like this, and then this ends up being my gusset plate. Go like this and go straight down here. And I wouldn't worry about here, because if I made the allowance here, the same allowance would be up there. So that ends up being the size of my gusset plate right there.
But how, like, I'm not too sure, how do we nail the top?
To nail the same way that you're going to nail the bottom, you're going to be putting 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, and this length here is going to be longer than that length here, so you don't have to worry about it.
And the distance, like, between the, like, where the two
right here?
Yeah, right there. Like that has to be 40, right?
Well,
Where the two pieces of wood connect.
no. Like, look at each piece individually. Like, when I'm looking at this one here, like I'm going to draw it up here so that you can see what we're doing. Hold on. So this one here, right? Once you decided that, for example, you're going to go cut straight up here like this. I should have drawn it a little bit better. Okay. I'll make the gusset plate a different color so that we can, let's see. Make it blue, okay? Okay, so for example, it's like you here we said you're gonna go straight up, you're gonna hit here like this, okay? You're gonna come down like this, okay? Then right here you're gonna go straight up. You see, that's your gusset plate.
Mm-hmm.
Fair enough? Well, now here I keep a distance of 40, right? Always parallel to the grain, a distance of 40, and then I just keep making distances of 60. And if I can put my 54 nails in here, and I sure can, because if you look at this length here is shorter than this length here. Do you agree?
Mm-hmm.
Okay. So here what the carpenter is going to do, he's going to do this. He's just going to take this, divide the spacing. For example, if he knows that he put, for example, 7 rows in here, he's going to divide this into 7 equal rows, and he just nailed this. All you have to worry about is that when you specify the size of this gusset plate, when he puts his nails, he can respect all those minimum distances.
Mm-hmm.
So you don't have to worry about like if this here is shorter than this, and if this is 2x6 and that's 2x6, I know I'm getting an ample room to put my 54 nails in there also.
Okay.
Is that okay?
Yeah, but so
Like,
when we're
you don't like, in other words, you don't work this out and then all of a sudden you make a gusset plate go like that.
Mm-hmm.
You just go straight up and then you come down. Okay. I mean, this piece of plywood that you're saving gonna get scrapped anyways. It's just gonna end up in the wood pile. So what you're trying to do is you're trying to determine this length here so that you can cut this piece out of your plywood and get your gusset plate out.
So all we need to do is specify the bottom length or that longer length, right?
Well, the bottom length, because what's going to happen is that the carpenter is going to be from this bottom length, right? He'll be able to calculate what this length is here. He'll be able to calculate what this length is here, and then this length is going to end up being automatic.
Mm-hmm.
It's like I said, the carpenters all work with their squares. You understand? They'll be able to, with this ratio of 12 to 4. They know what this angle is with their square. You follow?
Mm-hmm.
So he'll be able to work all of that out. If he's a good carpenter, he should be able to work out all the geometry just by giving him one dimension and by giving him the slope of his member. Okay?
And this would be the same.
If you want to be nice, and if you're doing this on AutoCAD, you can also give him that length there. So it's up to you. Like Emily, the more information you give, and as long as the information is correct, more likely less mistakes are going to be made, right?
Yeah, for sure. Okay.
Okay. And don't forget, Emily, when they're doing this, okay, when they're doing this truss, right, what's going to happen is that they're going to, what they call a jig, they're going to set up like, they'll start mitering all the pieces of the bottom cord. They'll start, like the top cord. And then they'll have the whole truss basically fitted together without the gusset plates. And then the guy can actually, once you get him this dimension here, what he's going to do is going to take his piece of plywood, put it in between there, right? And then take his piece and slap it over there, and he'll be able to like draw underneath it and get the exact shape that he needs from his gusset plate. He can even do that. That's And if he doesn't know what that dimension is, you can, and he can't figure it out, he'll probably call you and ask what it is, and then you just go to AutoCAD. So that's what I'm saying with AutoCAD. If you want, you can actually give him that dimension. If you want to simplify his life, saying you can even give him that dimension. It's up to you. Give him whatever information you give, but you have to give him at least one. This is one piece of information here, and this is the other piece of information. So some people believe that you give the minimum amount of information that the guy calculates the rest so that you can minimize the errors. That used to be the old days. Now the new days with AutoCAD, if you draw everything accurately, or just give him the information, AutoCAD is going to accurately give him whatever he needs. So I'm from the school of thought that the more information you give, and as long as it's correct, the less of a chance that there's going to be a mistake down the road.
Okay, perfect. Thank you, Sid.
So you were trying to break your head on how to stick the nails in here. Is that what was your problem?
I honestly, I don't know what I was doing. Yeah.
Well, I looked at your drawing. I said, well, first of all, she's okay. So now you're telling me that you're putting 2x6 top and bottom. I can understand why you were starting with that. Okay, so I don't want to question that. And I said, it's better that we talk instead of me trying to answer by email, because we might be just going back and forth. Fair enough?
Would it be that I put a 2x6 as the bottom chord?
Yeah, well, we worked it out, and I think we ended up getting a ratio of 1.01 as opposed to 1. And trust me, that is 1 as far as I'm concerned. Especially that we've all double-checked our loads, we've all double-checked our analysis and everything. As far as I'm concerned, that's 1. You know, I don't want to like. I'm from the school that I can tell you how far off I can be off, that I can still consider to be acceptable, but I won't influence you guys. You understand? So.
But I can still keep what I have, right? Because I already worked out.
You're more than welcome to keep what you have as long as your calculations. You understand? You're just. See, I go through the calculations, then I look at your drawing. You understand? What I'm going to do is I'm going to make sure that your drawings reflect what you say in your calculations. So don't worry about that. Okay. Okay. So, ladies and gentlemen, any more? Like, either one. If you have any questions, now's the time. Otherwise, I'm just going to call it a day, and we'll talk to you guys Monday morning. This way you can spend some time doing your design for your project and stuff. We all good?
Take care, sir.
So you guys, unless you have anything else, like I have nothing else to share with you right now. And like I said, I will send you that last spreadsheet. And most likely, I don't know, like Monday, I'm just going to basically be reviewing the solution for the thing. And I have nothing more to say on the project. So guys, have questions for me, because I think I covered everything that needs to be covered in the wood as far as I'm concerned. And then after that, I'm gonna have to wait for you to. So, okay guys, so listen, stay well, stay safe, of course, most importantly. I don't know if you guys noticed, but hold on, I'm gonna stop this video.